All right, can you see my screen okay?
Yes, we can.
Okay, great. Well, thanks too, I'll reiterate what Todd said. Thanks to the team for putting this together. It's really great to share a lot of the neat things that are going on in offices across the region. And actually, Todd's case was kind of a pretty good warm-up. And thanks, Justin, for bringing the question up about spectrum width. So that's what we're going to look at in the next few minutes here is, can spectrum width be helpful, and to what degree in the tornado warning decision-making process? And the motivation for this came from conversations Pat Spoden and I had with Les Lemon over a decade ago, actually, that resulted in the publication of this paper, The Operational Uses of Spectrum Width. And specifically, what we wanted to do was take off in the direction, while this paper shows a range of ways spectrum width can be used, we wanted to take off in the direction of, can it be useful in the tornado warning decision-making process? So just a quick review of spectrum width for folks who might not be using it too much, although kudos to Jason Schauman and the TWIP folks for bringing spectrum width back into operational use with its importance of finding the updraft, downdraft convergence zone in QLCSs. But spectrum width was one of the 3 original Doppler moments we received when the radar network was developed. And what it is within the pulse volume, it's a measure of the velocity dispersion, or if you're thinking in a statistical sense, the variance of velocity within that pulse volume. And while there are engineering aspects that create spectrum width, for example, how rotation rate of the radar dish and whatnot, the primary producers are meteorological, being both wind shear and turbulence. So the goal here is to leverage that wind shear angle. One thing to always keep in mind, your standard radar data limitations and data quality issues apply. You know, your beam height and width as you get farther from the radar, the quality of the radar signal you get. The errors that we see operationally with the use of spectrum width in this context result mainly from overlaid echoes from range folding, or second trip echoes in the old parlance, and also in areas of low signal to noise ratio, or where you have weak reflectivity. So it's always good to look at spectrum width in context with your reflectivity and your velocity data, and also consider the environment your storm is in. So for the first part of the study, what we wanted to look at was the temporal trends and values of spectrum width maxima in mesocyclones and mesovortices that produce tornadoes, to see if there was any utility there in a diagnostic and warning decision-making process. This tornado, by the way, is the Fairdale, Illinois EF4, showing that we do occasionally get big tornadoes up here, but also we'll take a look at this in the radar data here shortly as well. So what we did is,
sorry to interrupt you, Ray, but we're getting some feedback on our microphone. So if everybody can just check to make sure that you're all muted, please. Thank you.
So what we did is we identified the tornado producing circulations and initiation times in our area, and we consider each new mesocyclone in a cyclic supercell, or each mesovortex in a QLCS that produces multiple mesovortices, a new circulation. We look at the half-degree spectrum width from 20 minutes before tornado initiation to 5 minutes after, and take the values associated with the circulation, and specifically look at the maximum value in the spectrum width maxima, the maximum bin in the circulation, and we tabulated that backwards in time. The data was then composited to assess the trends and absolute values. So we had tornadic storms from 2008 to 2016 that gave us 99 events. This includes cases where sales and AVSET were active and cases where we did not yet have sales or AVSET. A few of the cases had some data quality issues, which were almost all, well, a couple of them were range folding. We also looked at the EF scale, storm mode, and the distance from radar. Again, reiterating the importance to keep in mind when doing studies like this that radar data sampling issues need to keep in mind. And also, when the compositing technique can average out some details that might be critical to important cases while you're looking for the mean of what's important in all the cases. So if we take a look at this graph here, this is a number of spectrum width observations going back in time, starting from t = 0, which was tornado initiation time, going back to the left as far back as 20 minutes. And kind of the thing to point out here, obviously, as you get closer to tornado time, you find more observations. But the bars that are listed or that are shown in red there, that's data that's resulted from sales. So we can see the positive contribution that judicious use of sales can add to the warning decision-making process, and why that and also now MERL are important parts of the warning decision-making process. The observations by EF scale are shown here. Most of the tornadoes were EF1s, no 4s and 5s in this data set. We did have a couple of 3s and 2s, and this basically reflects our tornado climatology up in this part of the world. The observations by storm mode, interestingly, even though we're in QLCS land, 2/3 of our tornadoes came from supercells. Unfortunately, they're not all as easy to warn for as that Fairdale one I showed earlier. Also fortunate, most of them are EF1s, just like our QLCS tornadoes. The other category is made up primarily of landspouts. Observations by distance from the radar, we show a good distribution there, at least up until you get 90 nautical miles away from the radar. So we had some in that sweet zone, really close to the radar, and a pretty even distribution beyond that. So here's kind of the go-to slide. We take a look on the right, the black line shows the spectrum width values on the y-axis at time t = 0 relative to tornado initiation. And then we go back in time 20 minutes prior to tornado genesis. And what we see is that the mean values of spectrum width are pretty consistent and pretty high, between 20 and 25 knots. To put in perspective, the yellow lines are plus or minus 1 standard deviation. So we see that with tornadic circulations, high spectrum width values, as one would expect, in the upper teens all the way well up into the 30 knot range. Here's a standard box and whisker diagram. The box is your 75th and 25th percentiles there, your medium value of 26. So we see if you have a circulation with spectrum width values in the upper teens and higher, it's very likely has tornadic potential. Whereas if you have circulations with lower spectrum width values implicitly, the likelihood of tornadoes is much lower. We'll take a look at a couple examples here. This is an HP supercell just west of the office from April 2015. This is kind of a big picture view. Half degree reflectivity upper left, storm relative velocity on the right, spectrum width in the lower left, and CC in the lower right. We'll take a zoom into this, and a real close zoom in. We see a nice reflectivity thumb or hook. It's associated with a very tight circulation. That circulation was indicative of the narrow and intense tornado that was associated with this. Spectrum width values are quite high in the lower 30s here, and we do have a tornado debris signature as the tornado is ongoing in this event, even though the spectrum width maximum did provide lead time in this case to the occurrence of the tornado. I mentioned the Fairdale event, which actually occurred a couple hours after the one that I just showed. This is in north central Illinois, pretty classic supercell. The environment between our office and north central Illinois was subtly different. The mid-level instability was more substantial. We see a really decent hook, classic supercell structure, strong mesocyclone, a whole lot of spectrum width. What's interesting is with the CC, we see the low CC reflective of the inflow air being sucked into the storm, as the tornado has not yet formed at this point. But I show this case to illustrate that while spectrum width is useful, there are going to be many cases of supercells on this order where it's not going to be a major key to the decision-making process because your threat is obvious before you even get to the point of looking at spectrum width. If we take a look at a QLCS example from back in May 2015, we see the reflectivity in the upper left, a nice line break there, one of the confidence builders from the TWIP training. The storm relative velocity shows a quick switch in wind direction. The spectrum width in the lower left well illustrates that, the updraft, downdraft convergence zone, and nothing in the CC yet because we're pre-tornado. Zoom in on that really close, we see another tight circulation, just 2 pixels here. Very intense spectrum width associated with it. That spectrum width actually showed up 8 minutes prior to tornado genesis, and we would see in the next volume scan, which I didn't show here, TDS would develop. Another QLCS, this is a neat example of a comma head tornado, very intense mesocyclone, a strong spectrum with maxima here. We're 85 nautical miles from the RDA here. And if TJ Turnage is on, I took a look at NROT here. We see in blue the positive NROT bookended by 2 negative NROT minima. Pretty interesting, very strong circulation in the comma head. These latter 2 cases fall into the high shear, low cape category. So to kind of summarize what we found from the first part of this study is that tornadoes are very frequently associated with high spectrum width values, roughly 20 knots and higher. There's no clear spectrum width max trend prior to tornado initiation. Pat and I thought from some of the cases we had observed that maybe we'd see a ramping up of values, but actually instead what we found is that they're already at high values. The spectrum width maxima are not typically observed with land spouts. This is likely because of the resolution, the size of land spout circulations, and the radar's inability to well observe them unless they're really close to the radar. And another important thing here in utilizing spectrum width is the importance of a well-designed color curve to enhance the visibility of these key values. Really makes observing the events much easier. Sometimes we find that the spectrum width max is actually easier to track than the velocity, especially when you get side lobe contamination, and it's unclear what's going on. You know, at a quick assessment of the velocity, the spectrum width can help guide you through that. I mentioned already the sales and AVSET greatly enhance the amount of data available for evaluation. That combination, especially for the high shear, low cape storms, which are low topped, is really important. And we didn't find any relationship of spectrum width maxima to EF scale. So stronger tornadoes do not necessarily have higher spectrum width values, though the sample size for EF3s and higher is rather small. Storm mode, the spectrum width values for supercells was pretty equal to what we see with QLCSs. And notable is that there was no difference in values as you get farther from the radar. So what do we have at this point? Spectrum width is another useful tool in the toolbox for helping identify tornadic storms. But the question then becomes, does spectrum width help discriminate tornadic from non-tornadic storms? That's really kind of the gold level that we're looking to get to. So part 2 of the study was to explore the temporal trends and values of spectrum width max in non-tornadic mesocyclones and mesovortices to see if spectrum width values could be used to discriminate the tornadic from non-tornadic circulations. Not necessarily an easy study to define because there's so many circulations out there when you're looking at many years of data. So what we did to kind of pare it down is we took false alarm tornado warnings we've issued, and we've set that tornado warning issuance time at t=0. The idea here is that the forecaster had seen enough in radar data and environmental data and storm reports, spotter reports and whatnot to be concerned enough to issue a tornado warning. So we wanted to evaluate, again, the spectrum width up to 20 minutes prior to that time, basically following the same approach as we did in part 1. We had 92 events between 2008 and 2016. Again, sales and AVSET, non-sales and AVSET cases were involved. We had a few cases with data quality issues, again, range folding being the main one, and repeating, again, the standard radar data sampling issues you need to keep an eye on, and the compositing technique, averaging out important details, is something to keep an eye on. So again, with this data set, much like our climatology, about 2/3 with supercells and 1/3 with QLCSs. This was kind of an interesting finding in itself, as our false alarm rate for tornado warnings really doesn't differ between storm mode. I think there's a perception out there that perhaps we get a lot more false alarms with QLCSs than supercells, but not the case for this data set. Also, interestingly, they were not distributed equally by range. Most of our false alarms occurred between 31 and 60 nautical miles, and that's kind of a point that deserves greater study. And the results, if this looks like the slide I just showed a few minutes ago, it's not at all too different. The mean values, starting with your tornado warning issuance time on the right and your y-axis being your spectrum width values, the red line showing the mean. And so the non-tornadic circulations had spectrum width values on the order of what the tornadic signatures had. We see values between 20 and 25 knots, plus or minus 1 standard deviation, going from the upper teens into the lower 30s. Box and whisker diagram is virtually a clone of what we saw from the results in part 1. The median value slightly lower at 24, the 25th and 75th percentiles encapsulated between 19 and 29. So I didn't do a statistical analysis on it, But when you look at these two box and whisker diagrams, it's hard to believe that there's any statistically significant difference between the two populations. So what do we conclude here is that spectrum width is not useful for discriminating tornadic from non-tornadic QLCS or supercells, at least based on our FAR tornado warnings. Most of our FAR tornado warnings, though, did not include spectrum width values that were low. So we may be, since this is something we've been looking at for the last decade or so, this may be something that's actually weaved into our decision making, and that we're not issuing tornado warnings on those low spectrum width value storms. So you can add spectrum width to the tools that help identify tornadic potential, but don't discriminate tornadic from non-tornadic storms. This includes VR shear, azimuthal shear, some storm structure, the appearance of weak echo regions or bounded weak echo regions, etc. So unfortunately, no help there. So to kind of wrap up, the question becomes, how can we manage this data operationally? And what I've put together here, this is a 16 panel. At this point, it's zoomed out looking at the QLCS on the left, but typically this is zoomed in closely for storm scale analysis. We have the reflectivity in the left column, your spectrum width and base velocity toggle in your second column, your spectrum width and KDP are in the third column, and then your CC and ZDR in the fourth column at right. At the top is your half degree, 0.9, 1.3, and 1.8. And you'll find that this type approach allows you to look at trends in the data, which I think is an underutilized warning decision-making tool. You can get in easily, look at spectrum width. You can toggle back and forth to see differences between storm appearance and velocity and storm relative data. And then you got your CC and ZDR for your TDS signature. And this curve is really great. We find in high shear low CAPE events, when we invoke MERL, typically for storms that are close to the radar, you can see the updated information immediately. But for those occasions to where you want to look at higher elevations, especially as you get close to the radar, it's best to use this in combination with a panel combo rotate so you can assess some of those higher tilts that might not appear on the 16 panel. And also the MRMS volumetric products are a handy complementary tool as well. Especially when you get into your cone of silence and you're relying on neighboring radars to kind of help fill that gap. And then to maintain your bigger picture SA, half degree reflectivity velocity SRM loop is good. So you can really pare down in a very systematic way the amount of radar data you look at so that you can give the data the due time it needs for assessment. And with that, I'd be ready to take any questions.